Before we look at specific semi-parametric models, I want to introduce the general components that a semi-parametric model is derived from. So we've just looked at polynomial regression. We've seen that it can produce flexible, smooth curves, but it's fitted globally. We talked about that. Conversely, the step functions are fitted locally, but they produce bumpy fits. And as I said previously in the last part of the lecture, semi-parametric regression is essentially going to bring these two elements together. It's going to bridge these differences by providing adaptive local smoothness. So instead of fitting a high degree polynomial over the entire range of x, we're going to fit separate low degree polynomials over different regions of x, essentially within intervals defined by cut points. And that's how it merges these ideas. The idea of polynomial regression and step functions are going to essentially be merged. Now, as mentioned in the introduction to the lecture, terminology concerning what constitutes a parametric, non-parametric or semi-parametric model is somewhat inexact. And what we're going to do here is just almost quite loosely define, and I've not put it in a definition, formal definition per se, is we're going to define a semi-parametric model to be one that makes a priori minimal assumptions on the functional form of relationship between response and covariates. So with a semi-parametric model, we're not going to say that we think the relationship's linear, non-linear, linear, quadratic, cubic. We're going to allow the data to some extent to tell us what the relationship looks like. So in a semi-parametric model, we often assume that relationship take the form of an unknown smooth function that's going to be revealed through analysis of the data in a very flexible fashion. And that's the key defining feature of a semi-parametric model, is flexibility, which we often achieve via specification using some or all of the following three components that make up a semi-parametric model: basis functions, splines, and knots. And we'll now just cover what each of them mean. So first, basis functions. Basis functions, which we're going to denote B subscript I, are a family of functions or transformations that can be applied to independent variable x. So using bold B to denote a set of basis functions, we have b1x, b2x, bkx, where B is a vector valued function, vector valued, so that's why it's in bold. That vector value function is defined on the space of x. And the point we're going to use in semi-parametric regression is that a linear combination of basis function can provide a systematic way to approximate other complex unknown functions. So we're going to use the basis functions, or a linear combination of them, as an approximation to the unknown function that we want to estimate. And so to give two examples, the basis function for the polynomial regression model, the jth basis function is simply the jth power. And for step functions, the jth basis function is the indicator function that decides whether whether cj is less than or equal to x, less than or equal to cj plus 1. So that's how we'd write the basis functions for those models that we just looked at, the functions we just looked at, polynomial function and a step function. Now, why do we want basis functions? Well, by specifying our model for y in this new space bx rather than x itself, we aim to write it in a way that captures intricate patterns in the data without assuming a specific parametric form. That's why we're being semi-parametric. A priori, we're going to try and make minimal assumptions about the parametric form of the relationship between x and y. So we plug our basis functions into the regression equation. That gives us this design matrix here. You can think of it a little bit like a transformation, but of course in this case B is vector valued, and it's been multiplied through by the betas, so b1 times the first basis function, b2 times the second basis function, and these are all added up to give us our approximation. Now the basis functions we're going to assume are fixed and known, so the basis functions are chosen a priori, and we're going to look at several ways in which we can do that. And it's worth emphasising that although we're treating the problem as linear, actually, you can see here linear in parameters still, although deviating in the sense that we're not being so prescriptive about things. The solution as a function of x is actually non-linear, although we can write the problem and treat it as linear. And that's one of the beauties of how these models work. Second definition, so the first is basis function. The second definition is just a specific type of basis function that we call a spline. And a spline is a piecewise polynomial form used to model smooth unknown functions. So it's a type of basis function specified in piecewise polynomial form. Splines provide flexibility and local control over the shape of the curve. And we'll see what this looks like in a minute. And definition 5 we call knots. Knots, which we're going to denote as kappa 1, kappa 2 up to kappa k, are specific points on the domain of x that form the boundary point of the adjacent intervals over which the splines are specified. So these points are going to define where pieces of spline join or change direction. So I hope you can at this point see how we're combining polynomials, a polynomial piecewise form as a spline, and cut points in the form of knots, where we're going to join these splines up. So essentially, the splines are going to have loose ends within each interval, and we're going to use the knots to connect them. And specification via splines and knots allows for smoothness and local adaptability without requiring a high degree polynomial across the entire range of the data. So that's how it nicely merges the good property of step functions, which says that they're local, and the good property of polynomials, which is that they're smooth. We're just going to bring these two things together. Just to give you a visual illustration, the figure below illustrates the idea of representing a function in terms of basis functions using, in this case, a polynomial basis. It's actually of degree 4. The bases are shown in these panels here, 1, 2, 3, 4, and 5. So the first basis is just a constant, 1. That's the intercept. The second basis is linear in x, that's a line. The third basis is quadratic in x, it gives us this line. The fourth basis is cubic in x, it gives us this line. And the fifth basis is quartic in x, and it gives us this line. And when we sum all of these together, given the coefficients beta 1, beta 2, beta 3, beta 4, beta 5 that are going to multiply through on these basis functions, then that's the curve we get at the end. So the basis functions then multiply by each real value parameter beta j and sum to give that final curve that's shown there. And of course, by varying those beta j's, we can vary the form of this final curve actually to produce any polynomial function of order 4 or lower. I want to just make one final point in this section of the lecture on knots. These diagrams here show a linear spline regression fix. That's a spline of degree 1, and we'll explain later in the lecture what that means specifically. But in this case, the number of knots that we're using to connect the different splines are increasing from 2 knots here, 1 here and 1 here. I think 3 knots here, 1, 2, 3, then many more knots, and then a very great number of knots. And what you can see is that as the number of knots increases, the fit to the data improves. It fits the data better. Particularly this model here is fitting the data very, very nicely. And it's becoming more smooth actually. But at the risk of overfitting, and in this final model here, it starts to get very, very wiggly towards the outer intervals of the data. And that's what you call overfitting, because what we're not necessarily able to do here is distinguish noise, that is random error, from the fit of the curve, that is the signal. So choosing the number of knots is actually an important process, as we'll see later. It can improve the fit to the data, but we've got to be careful of this problem of overfitting.